Okay, so I'm going to talk a bit about planarity. So for this, I wouldn't say you have to read this before you watch the video, but this goes along with section 10.1 in the book. And so let me start by talking about something that you might have seen before. It's called the three utilities problem. So I've drawn basically 6 vertices, and we're imagining that these top 3 are representing 3 utilities, like water, electricity, and I don't know, cable. And then down here I have 3 houses, and you're supposed to connect every house to every utility, but you don't want to cross any edges. So basically what we're trying to do is we're trying to draw K33. I've got 3 vertices up here and 3 vertices down here, and everything up here needs to be connected to everything down here, but I need to draw this without edges crossing each other. And you can try, I mean, it's not too hard to draw the first few. I mean, so this utility is connected to all 3 houses, and then I can connect this to all 3 houses as well, because I don't have to use straight line segments. I can go around like this. And then what's the third house gonna do? The third house, or sorry, I get this is the third utility, but I need to connect this one to all 3 down here. And I can do this one, and I can hit that one because if I'm sneaky, I can go in like this. This picture's turning into kind of a mess, but there's just no way to connect this one to this one. That would be the last thing that I had to do, and there's no way in. So as it turns out, this problem is impossible. It's kind of designed to just, you can give it to somebody if you want to keep them busy for a while, because they're never going to be able to do it. But it's not completely easy to see why you can't do it. So somebody who doesn't know that it's impossible might actually try for a long time without realizing that that they need to give up because it's just not possible. So that's one thing we're going to see today. We're basically going to see a proof that that's not possible. And so this is basically what the subject of planarity in graphs is all about. It's about trying to draw a graph without crossing the edges. So a plane graph is a graph that's drawn in the plane, and I mean R2, that this is the Cartesian coordinates. It's like the XY plane with the, and you represent each vertex by a point in the plane, and you represent each edge by what we're going to call an arc. The edge doesn't have to be a straight line segment. Arcs are like the things that I was drawing. They don't have breaks in them. So, for example, I can't draw this last edge by just sort of like going up to here and then breaking and then picking up over here, because that's cheating. Can't have a break in it. But other than that, it's allowed to be curvy and bendy. So here's an arc that goes from the point U to the point V. It can even sort of like spiral around V a little bit, like that. And we're going to call those arcs. So a plane graph in general separates the plane into several of these things that we call regions, and regions are sort of an intuitive concept. So here's a picture of a plane graph. It has 4 vertices, and it has the edges that I drew, and as you can see, none of the edges are crossing each other. Oh, yeah. Before I forget, let me also mention an edge is not allowed to cross itself, of course. Like, you're not allowed to go like this or anything. Um, and then they're also not allowed to cross each other. Uh, but right, this separates the plane into three of these things that we're calling regions, and I put names on them. I'm calling this R1, this R2, and this R3. And it's kind of, by the way, R3 is like the entire outside. So R3 sort of goes forever. Um, of course, my page isn't infinitely big, but we're imagining that this is the plane, and the plane does go forever, and R3 would include everything, even 100 miles away. Um, so more formally, what are these things that I'm calling regions? They're subsets of course, this should be the plane, R2, such that any 2 points in the subset can be connected by an arc without crossing the edges of the graph. For example, if I pick 2 points in the region R1, like let's say over here, and then another one over here, I can connect this point to this point with an arc. I could even do a straight line, but that wouldn't be very much fun. I'll do a little wavy line. Without crossing any edges. I can get from here to here using an arc and without crossing any edges. And all of the points that I can reach, basically the points that can reach each other, I'm calling these all R1. I could not get from a point in R1 to a point in R2 without crossing an edge. But I can get from any point in R2 to any other point in R2 by using an arc. I can also get from a point in R3 to another point in R3 using an arc. And of course, if I went straight through, that would be no good because I would be crossing edges, but I'm allowed to go around like this. So, yeah, that's more formally what we mean by the regions. There are certain sets of points in the plane. Once you've drawn a plane graph, and if you look at the points in the plane, it's possible to get from certain points to certain other points using an arc and without crossing any edges of your plane graph. And on the other hand, it may not be possible to get from a certain point to a certain other point. If it is possible to get between 2 points, then they're in the same region. If it's not possible, then they're in different regions. That's how we define regions. And okay, so admittedly, this is like confession time. This part of graph theory at this point in this class, it gets a little bit of what we call hand wavy in math. So hand waviness is when, okay, you know, as math students, you have to learn very rigorous proofs, and you have to cover all your cases, and you have to dot all your I's and cross all your T's, and it has to be very proper. And once in a while, admittedly, and today's going to be one of those days, I probably present a proof, and maybe you think to yourself, he wouldn't let me get away with that. Sometimes learning math, we kind of have to be that way because we are, this is an introductory graph theory class, and there are certain things that we're sweeping under the rug. What we're sweeping under the rug here is a subject in math called topology. Topology studies a lot of these problems, like the plane and regions that are connected because you can get from any point to another point with an arc, and they go into all of this more formally. And by the way, I'm about to state a big theorem that is basically a theorem from topology that we're going to steal and use for graph theory. But yeah, so the reason why I'm going off like this is just to acknowledge that we are sweeping some stuff under the rug. I'm going to state the Jordan curve theorem without proving it. It's a theorem from topology. It's pretty intuitive. Like if I just like once I tell you what it says, it's going to seem obvious, which is kind of dangerous in math because sometimes statements that seem obvious actually require proof, and that proof can be really hard. Um, anyway, here's Jordan curve theorem. Here's how I'm going to state it. Let C be a plane graph that's a cycle. So I'm just talking about a cycle. Like as a graph, it's just a cycle, but I'm also calling it a plane graph. So I'm basically stating that it is drawn in the plane. So here I drew a picture, and again, just because I want to be creative, I didn't draw the edges as straight line segments. I drew them kind of wavy, but they are arcs. Let me draw this one a little bit better so it actually looks like it goes to the vertex. Okay. And all the Jordan curve theorem says is that this plane graph has exactly two regions. Roughly speaking, there's the inside and the outside. It seems so obvious, doesn't it? Any point inside here, or sorry, any 2 points inside here, I can get from one to the other. Any 2 points outside here, I can get from one to the other. If I pick a point inside and a point outside, then it's not possible to get from one to the other. There's exactly two regions. There's the inside and the outside. By the way, more formally, this one that I'm calling the outside, it's the unbounded region. It's the one that goes forever. The inside doesn't go forever. If I pick a point and just start moving in a direction, I'm eventually going to leave the region I'm in. But outside here, I can pick a point and pick a direction and go forever in that direction, and without ever leaving the region. That's why the outside is called the unbounded region. So that's an example of what I'm kind of calling hand waviness. I'm presenting this. It is a theorem. It is true. It is proven, but I'm not showing you the proof. And by the way, I think the origin of calling it hand waviness is basically that the professor is sort of acting like a magician and getting you to accept the proof by waving their hands as if they just casted a magical spell, and that that's supposed to be convincing. I think that's why they call it hand waviness. But anyway, that's just a bit of math culture for you, I guess. Here is another fact that I'm going to base and it's another thing that's going to seem obvious, but I'm not going to prove this. That if T is a plane graph that's a tree, so I'm saying that this is like as a graph, it is a tree. Meaning it's a connected graph, it doesn't have any cycles, and it is drawn in the plane. Then T has exactly one region. Because a tree doesn't really, in the sense that we're talking about, it doesn't really separate any point from any other point. It's possible for me to, there's really just one region. Pick any point, any 2 points around the tree or far away or whatever, and I can get from one to the other. I might have to go around the tree, but that's all I have to do. So any drawing of a tree really just has the one region. It's the unbounded region. Okay. So I hope you accept those facts that I stated, because as long as you accept those, then we can use them to rigorously prove things. So what we're going to prove today is Euler's formula, which is in the book. It's theorem 10.1 in the book. So here it is. It's about the number of vertices, edges, and regions in a plane graph. If you have a plane graph G and it has n vertices, m edges, and r regions, then n minus m plus r equals 2. So it's nice. I mean, for example, if you know what two of these numbers are, then this formula can be used to solve for the last one. So let's try to prove it. So the proof is going to be on by induction on M. And so when I say induction on M, I mean the other variables could be anything. Like n could be anything and r could be anything. Well, anything that makes sense, right? Like we're talking about a graph with n vertices, so n is an integer that's at least 1, and r is an integer that's at least 1. But other than that, they could be anything. And we're going to do induction on m. So there's a funny thing about this proof, which usually for induction you need a base case and an induction step, right? And your base case is typically it's the smallest value of the variable that would ever make sense. And usually the base case is either when it's 0 or 1. So you might think that the base case is going to be when m equals 0 or when m equals 1. But those wouldn't quite make sense. What we have to do is we have to think about what we're assuming about the graph. G is a connected plane graph. So let's think about what's the smallest m could be, and keep in mind m is the number of edges for a connected plane graph. And what I'm going to tell you here is that m needs to be at least n minus 1. Why is that? Well, this would be the number of course, n minus 1 we recognize as the number of edges in a tree that has n vertices. In other words, a spanning tree. Since G's connected, G contains a spanning tree, so it must have at least the number of edges that would be in a spanning tree. So m is at least n minus 1. That's going to be our base case. Because once again, we're doing induction on m, and the base case should be the smallest value of m that makes sense, which would be n minus 1. So that's why it's the base case. And so let's think about it. Well, if it's n minus 1, then that means that G just is a tree. Like G has exactly the number of edges that its spanning tree would have. In other words, there's no other edges. It is just the tree. And what do we know about trees? A drawing of a tree has just one region. That was one of the facts that I stated. So G's a tree. That means it just has one region, and so now we check the formula. We go n minus m plus r. And remember that m is n minus 1 and r is 1. So I go n minus m plus r, and I simplify it, and the n's cancel, and I get 2. And that's what I'm supposed to get, so I'm happy. What about the induction step? For the induction step, I assume that m isn't that we're not in the base case. So m is bigger than this, so m is at least n now. And that means that G isn't just the tree, that G has at least one additional edge on top of what the spanning tree has. So in other words, G has a cycle. Like if you take a tree and you start adding more edges to it, you make cycles. So G has a cycle. And here I drew a little picture of what G might look like. And what I'm going to say is that any edge on that cycle has two different regions touching it. Like, say, let me look at this edge. There's this region and this region. In other words, one of the regions touching this edge is on the inside of the cycle, and the other region touching this edge is on the outside of the cycle. They're two different regions. So what we're going to do is we're going to imagine removing one of these edges, because this is how induction works. We're doing induction on M, which is the number of edges. So typically a proof by induction should involve considering a graph that has one fewer edges. So I'm going to imagine removing one of these edges. I'm going to let E be one of the edges on the cycle, and consider the graph G minus E. So of course, that would have M minus 1 edges. And how many regions would it have? Well, as we just discussed, this edge has two different regions on one side and the other side. And if we removed that edge, all that would do is it would turn those two regions into one region. Suddenly, before I remove that edge, these 2 points are in different regions because I can't get from here to here without crossing an edge. But if I removed this, then I could go straight from there to there. These two different regions become one single region. So the number of regions would go down by 1 if I removed that edge. So what do we know? We're considering a graph, G minus E. It has fewer edges, and so it has M minus 1 edges, and it has R minus 1 regions. And so we're assuming, because this is induction on the number of edges, we're assuming that the formula is supposed to be true for any graph with M minus 1 edges. So I go, and I have to be careful here, because the formula is supposed to go N, which is still N, like the new graph. I didn't remove any vertices, so it still has N vertices. And then I'm supposed to subtract the number of edges, which is now this, and then I'm supposed to add the number of regions, which is now this, and that's supposed to be 2. But then if I just simplify this, basically a 1 cancels a 1, and I get that N minus M plus R equals 2. In other words, the original number of vertices in our original graph G minus the original number of edges plus the original number of regions is 2, which is what we wanted. Okay. So, right, what we're going to get into now is talking about which graphs can and cannot be drawn in the plane. And not all of them can. As we talked about in the very beginning, we're going to see that the bipartite graph K33, like we were trying to draw in the utilities problem, K33 cannot be drawn in the plane without crossing edges. And so let's start talking about why that might be. So first of all, I'll give you a quick definition. A graph G is planar if G can be drawn as a plane graph. And this is a subtle distinction. Typically, when we're looking at these pictures of graphs, we tend to think of the graph as the same thing as the drawing of the graph. But formally, sometimes it makes sense to draw a distinction between the graph itself and a particular drawing, especially because a single graph might have many drawings. Like K4, here I drew K4, but I drew it with crossing edges. Here I drew K4 again, and it doesn't have crossing edges. So K4 is a planar graph because K4 can be drawn as a plane graph if you draw it this way. It can also be drawn breaking the rules. It can also be drawn with edges crossing. But just because you can draw it in a bad way doesn't make it non-planar. The fact that it has a good drawing, and when I say good, of course, I mean without crossing edges, that's what makes it a planar graph. So K4 is planar. As we're going to see, and as I've mentioned a few times now, K33 is non-planar. We still have to justify that. But I also want to call your attention to K5. I can start trying to draw edges. So there's some, but then, you know, I still have, if I just, of course I could finish by just drawing a star like that, but that would cross edges all over the place. So maybe I can draw a few of them, like I can draw this one, and what else is there? This one needs to be connected to this one, and I kind of have to go around like this, but I'm not stuck yet. What else? This one needs to connect to this one. I can go around like this, but then I need to connect this one to this one, and I'm trapped. I can't go through here because there's this edge in the way. I can't, you know, I can't go through here because I would be trapped in this area. And there's just no way for me to get from here to here. Of course, I could think, well, what if I backtrack? What if instead of going around this way for this edge, what if I went around that way? And you can try different things, but as it turns out, nothing's going to work. So as we're going to see, not that this is a proof yet, but we're going to see that K5 is non-planar. All right, and actually, I'm going to make this a second video.